Right now, as you listen to these words, there are worlds beyond our wildest imagination spinning through the cosmos. Planets where it rains molten glass sideways, where diamonds fall from the sky like snow, and where the very air glows with auroras that stretch across entire continents. The secret lives of these distant worlds are finally being revealed, and what we're discovering is reshaping everything we thought we knew about planets and their possibilities. In the past few years, the James Webb Space Telescope has revolutionized our understanding of exoplanets, those worlds orbiting stars other than our Sun. Just this year, Webb detected silicon monoxide gas in the hellish atmosphere of WASP 121b, a discovery that has never been made before on any exoplanet. This finding gives us our first glimpse into the complex chemistry occurring in the scorching clouds of these distant worlds, where temperatures soar to over 4,000 degrees Fahrenheit. But the diversity of planetary worlds extends far beyond the hot gas giants. Webb has also peered into the atmosphere of tidally locked planets, worlds where one side permanently faces their star, while the other remains in eternal darkness. On these worlds, scientists have discovered that the boundary between day and night creates perpetual sunrises and sunsets, with atmospheric currents that create weather patterns unlike anything on Earth. The morning side of these planets can be hundreds of degrees different from the evening side, creating winds that race around the planet at thousands of miles per hour. Perhaps most intriguing are the discoveries of planets with extreme weather systems that make Earth's most violent storms look gentle by comparison. On HD 189733b, astronomers have detected glass rain that falls horizontally at speeds of over 4,000 miles per hour. The planet's cobalt blue color, which might seem beautiful from a distance, is actually the result of silicate particles in its atmosphere that create this deadly precipitation. The planet's day side reaches temperatures of 1,700 degrees Fahrenheit, while hurricane-force winds transport this heat to the night side, creating a complex atmospheric dance that has been ongoing for millions of years. The study of these exotic worlds isn't just about cataloging strange phenomena. Each discovery teaches us something fundamental about planetary formation and evolution. For instance, the detection of water vapor in the atmosphere of ultra-hot gas giants like WASP-18b reveals how atmospheric chemistry can survive in the most extreme conditions. These findings challenge our understanding of what constitutes a habitable environment and expand the possibilities for where life might exist in the universe. The atmospheric compositions we're discovering on these distant worlds read like a chemist's fever dream. Some planets have atmospheres dominated by vaporized metals, where iron and magnesium exist as gases rather than solid materials. Others have clouds made of corundum, the same mineral that forms rubies and sapphires on Earth. These exotic atmospheric compositions result from the unique formation histories of each world, influenced by factors like their distance from their host star, the composition of the original disk of material from which they formed, and their interactions with other planets in their systems. As we continue to explore these distant worlds, each new discovery adds another piece to the puzzle of planetary diversity. The secret lives of these planets are teaching us that our solar system, with its relatively orderly arrangement of rocky inner planets and gas giants farther out, may be the exception rather than the rule. The universe is filled with planets that exist in configurations we never imagined, following rules we're only beginning to understand. The revelation of just how diverse planetary worlds can be has emerged from one of the most remarkable periods of discovery in astronomical history. Over the past 2 decades, we've gone from knowing of just a handful of planets beyond our solar system to cataloging over 5,000 confirmed exoplanets, with thousands more candidates waiting for confirmation. Each of these worlds tells a unique story of formation, evolution, and the complex interplay between stellar energy and planetary atmospheres. The story begins with the fundamental question of how planets form. In our solar system, planets formed from a disk of dust and gas that surrounded our young sun about 4.6 billion years ago. This process, called accretion, gradually built up larger and larger objects through gravitational attraction and collisions. But as we've discovered other planetary systems, we've found that this process can unfold in dramatically different ways, leading to planets that exist in configurations we never anticipated. Take the class of planets known as hot Jupiters. These are gas giants similar in size to Jupiter, but orbiting incredibly close to their host stars, completing full orbits in just a few days. The existence of these planets initially puzzled astronomers because our models of planetary formation suggested that gas giants should form farther from their stars, where it's cool enough for ices to condense and provide the solid cores needed for gas capture. The discovery of hot Jupiters revealed that planets can migrate inward from their original formation locations, spiraling closer to their stars through gravitational interactions with the disk of material from which they formed. This migration process creates some of the most extreme conditions found anywhere in the universe. On these hot Jupiters, the side facing the star can reach temperatures exceeding 4,000 degrees Fahrenheit, hot enough to vaporize most metals. The day-night temperature difference creates powerful atmospheric currents that transport heat around the planet, but these currents often can't keep up with the intense stellar heating, leading to dramatic temperature variations across the planet's surface. Recent observations by the James Webb Space Telescope have revealed the intricate chemistry occurring in these extreme atmospheres. On WASP 121b, for example, the upper atmosphere is so hot that water molecules break apart into hydrogen and oxygen atoms. The planet's atmosphere contains exotic compounds like gaseous iron and titanium, elements that exist as solids under Earth conditions, but become gases in the intense heat of this world. Even more remarkably, the temperature gradient in the atmosphere creates different chemical processes at different altitudes, leading to a complex vertical structure that varies dramatically from the scorching upper atmosphere to the slightly cooler lower regions. The diversity of atmospheric compositions extends far beyond the hot Jupiters. Scientists have discovered planets with atmospheres dominated by carbon monoxide, methane, and even exotic compounds like hydrogen sulfide, which gives some planets their distinctive pungent odor. The recently studied exoplanet LTT-9779b, an ultra-hot Neptune located 262 light-years away, has provided insights into how planetary atmospheres can survive in the most hostile environments. This planet shouldn't exist according to our current understanding, because it orbits so close to its star that any atmosphere should have been stripped away long ago, yet somehow it maintains a substantial atmosphere, suggesting that atmospheric retention mechanisms are more complex than we previously thought. The James Webb Space Telescope has also revealed the phenomenon of atmospheric asymmetry on tidally locked planets. These worlds, where one hemisphere permanently faces their star while the other remains in eternal darkness, create unique atmospheric dynamics. The hot day side drives powerful winds that attempt to transport heat to the cold night side, but the efficiency of this heat transport varies dramatically between different planets. Some tidally locked worlds show significant day-night temperature differences, while others achieve surprisingly uniform temperatures across their entire surface. The weather patterns on these distant worlds challenge our earthbound understanding of meteorology. On HD 189733b, the famous glass rain planet, the atmospheric dynamics create silicate particles that condense into tiny glass spheres in the upper atmosphere. These glass particles are then caught up in the planet's powerful winds, which can reach speeds of over 4,000 miles per hour, creating horizontal precipitation that would be deadly to any hypothetical observer. The planet's characteristic blue color comes from the scattering of light by these silicate particles, similar to how Earth's blue color results from the scattering of light by molecules in our atmosphere. Perhaps even more exotic are the planets where the atmospheric chemistry creates conditions that seem almost magical. On some worlds, the combination of high temperatures and specific atmospheric compositions leads to the formation of clouds made of vaporized metals. These metallic clouds can produce precipitation of liquid iron or even more exotic materials. The temperatures and pressures in these atmospheres are so extreme that familiar materials behave in ways that seem impossible under Earth conditions. The study of these extreme worlds has profound implications for our understanding of habitability. The traditional concept of the habitable zone, the region around a star where liquid water could exist on a planet's surface, is being expanded and refined as we learn more about atmospheric dynamics and heat transport. Some planets that orbit outside the traditional habitable zone might still maintain habitable conditions through atmospheric greenhouse effects, while others within the habitable zone might be rendered uninhabitable by atmospheric loss or extreme weather patterns. The role of stellar activity in shaping planetary atmospheres has emerged as a crucial factor in determining the long-term evolution of these worlds. Young stars are often much more active than our Sun, producing powerful stellar winds and frequent flares that can strip away planetary atmospheres. The James Webb Space Telescope has observed several examples of planets in the process of losing their atmospheres to stellar radiation, providing real-time observations of atmospheric evolution in action. One of the most significant discoveries has been the detection of atmospheric variability on exoplanets. Just as Earth's weather changes over time, these distant worlds show evidence of atmospheric changes that occur over periods ranging from hours to years. Some planets show evidence of seasonal variations as they orbit their stars, while others display more chaotic atmospheric behavior that might be driven by complex interactions between atmospheric circulation and stellar heating. The chemical signatures detected in these atmospheres also provide clues about the formation history of planetary systems. The presence of certain elements and compounds can reveal whether a planet formed close to its current location or migrated from elsewhere in the system. Water vapor, for example, is more abundant in planets that formed farther from their stars, where ice could initially condense. The detection of water vapor in the atmospheres of hot gas giants provides evidence for planetary migration and helps astronomers understand the dynamic processes that shaped these systems. As our observational capabilities continue to improve, we're beginning to detect smaller, more Earth-like planets around other stars. These worlds present new challenges and opportunities for understanding planetary diversity. Rocky planets can have a wide range of atmospheric compositions, from thick Venus-like atmospheres dominated by carbon dioxide to thin Mars-like atmospheres that have lost most of their original gas content. The boundary between these different atmospheric types depends on factors like planetary mass, distance from the star, and magnetic field strength. The discovery of planets around different types of stars has further expanded our understanding of planetary possibilities. Planets orbiting red dwarf stars, which are smaller and cooler than our Sun, face unique challenges related to stellar activity and tidal locking. These stars can remain active for billions of years, longer than Sun-like stars, potentially affecting the long-term evolution of planetary atmospheres. At the same time, red dwarf stars are much more common than Sun-like stars, meaning that planets around these stars might represent the most common type of planetary environment in the galaxy. The implications of these discoveries extend far beyond academic curiosity. Understanding the diversity of planetary atmospheres helps us better appreciate the unique conditions that make Earth habitable and the factors that might threaten that habitability. The extreme greenhouse effects observed on some exoplanets provide insights into how atmospheric composition can lead to runaway climate change, while the atmospheric loss processes observed on other worlds illuminate the mechanisms that could potentially affect Earth's atmosphere over geological timescales. Each new discovery adds another layer to our understanding of planetary science and the factors that make worlds habitable or hostile to life. The secret lives of these distant planets are revealing that the universe is filled with worlds that exist in configurations we never imagined, following physical processes that push the boundaries of what we thought possible. As we continue to explore these distant worlds, we're not just learning about planets. We're discovering the fundamental principles that govern the behavior of matter and energy in the most extreme environments the universe can create. The ongoing exploration of exoplanetary atmospheres represents one of the most active and rapidly advancing fields in astronomy. With each new observation, we're adding to our understanding of how planets form evolve, and potentially harbor life. The secret lives of these distant worlds are teaching us that the universe is far more diverse and dynamic than we ever imagined, filled with possibilities that challenge our assumptions and expand our understanding of what it means to be a planet in the cosmos.